Okay, so I think we're almost up to 30 people who've joined the second IBS Journal Club, and I'd like to welcome you all. My name is Jim Todd. I'm a professor of applied biostatistics at the London School of Hygiene and Tropical Medicine. Just want to say welcome to everybody, and some of you may have attended the first Journal Club about 2 months ago when we had a very interesting discussion around the paper then. And this time we're going to have a very interesting discussion with the paper by Patrick Kimes. And what I want to do is just to reiterate that we'd like to, the ground rules for the club, which is to keep the discussion simple so that we don't lose anyone. We don't have to be too technical in this Journal Club. We just need to try to enable some understanding of the points that we make. If you do have questions, you can raise your hand and you can keep those questions short, make your comments short and concise to the point. In that way we can get the best out of it. Remember to speak slowly and clearly. Both the internet in some places is a little bit suboptimal, and perhaps English may be not the first language for many people. Let's be constructive. Let's build a discussion in a positive way so that we all get something out of it and respect others in that. Raise your hand if you want to speak, and if you're not speaking, then mute your microphone so that we don't get background noises on that. The papers and the other supporting documents are on the left-hand side under the links tab, so you can get the paper by Patrick Kimes, or you can get the presentation that's going to be made and other documents there. All of this is being recorded, so please be aware that what you say will be recorded and made available afterwards. So if you can, make sure you mute your microphone when you're not speaking. Any questions, please put them in the chat, and then we'll try and answer them, or we'll try and continue with the discussions in other ways. Okay, that's all I'm going to say, and now I'm going to hand it over to Patrick Kimes, who has got the... Oh, any questions, first of all? Questions? No, questions are for later, I think. I'm going to hand it over to Patrick and ask him if he wants to take us through his paper, which has been circulated and is the statistical significance of hierarchical clustering. Okay. So let's just see whether that now will be changed so that Patrick will take over as leader, and then he'll take us through his slides as well. But if there are any questions, let me know. Raise your hand and yeah. Okay, hand it over to Patrick.
Okay. Great, thank you, Jim. I'd like to first just start off by thanking the organizing committee for the Journal Club for giving us this opportunity to talk about this paper that was recently published in Biometrics. So this image that you see on this first slide is what we call the Old Well at the University of North Carolina, which is where I was at the time that this work was done. So this was joint work with Yufeng Liu, Neil Hayes, and Steve Marin at the University of North Carolina, where I completed my dissertation. Currently, I'm a postdoctoral fellow at the Dana-Farber Cancer Institute in Boston, Massachusetts. So this paper, Statistical Significance for Hierarchical Clustering, is really a methods paper. And so what I'd like to do in approximately the next 20 minutes or so is sort of outline the problem that we were looking to solve with our method, and describe the method that we proposed, as well as sort of give a brief overview of some of the theoretical and empirical results that we derived for the method. And please let me know if you have any questions. Hopefully I'll be able to explain things in a reasonably understandable manner, but if anything comes up, please let me know. So just to get started, what I'd like to do is talk about the question of clustering. So in clustering, what people typically observe is a set of observations, x1 through xn, in some sort of covariate space. In this simple example that I'm showing here, the space is just a two-dimensional Euclidean space, so just R2. And the task, having observed this data, is to partition it into what we call clusters, these homogeneous subpopulations or groups within the data. So a common way of doing this is using something called combinatorial algorithms. So the most commonly used and probably most well-known example of this is something called k-means clustering. So k-means clustering is an algorithm where you define this pairwise observation dissimilarity as well as a number of clusters k. And what we try to do is partition these observations into these k groups. So in the case of k-means clustering, the dissimilarity is chosen to be Euclidean distance. What it ultimately comes down to is minimizing this within cluster sum of squares. So examples of what you might observe if you use k-means clustering with 2, 3, and 4 clusters is what's shown on the left. So aside from combinatorial clustering algorithms, another class of algorithms that's fairly well known and used is hierarchical clustering methods. And this is really the focus of this paper and this talk. And so with hierarchical clustering, what we need to do again is to define this dissimilarity metric between observations. But instead of defining a number of clusters that we're interested in K, we have an extension of dissimilarity to clusters called linkage. So examples of linkage functions for dissimilarities for pairwise clusters might be the average distance between observations in the two clusters, or the average, the minimum dissimilarity between observations in these two clusters, or the maximum. And so the way hierarchical clustering works is we typically start off with all the observations in separate clusters, and we iteratively join them together to get our hierarchical partition. And one of the reasons why hierarchical clustering has been so popular is it can be intuitively visualized using something called a dendrogram. So for this toy example of 5 observations, the way hierarchical clustering might work is we first notice that 3 and 5 are the closest, so we bring them together in this dendrogram, or this binary tree. So what you see now is observations 3 and 5 are brought together at a height equal to their linkage, or their dissimilarity. And next what we do is we bring 4 and 2 together at their linkage or dissimilarity. And then we next bring 1 to 4 and 2 because it's the next closest. And finally, we bring everything together. So this is what we call a dendrogram, a binary tree, to represent hierarchical clustering. Now with hierarchical clustering, you can get any number of clusters if you simply cut this tree at any height. So if we cut the tree at, say, linkage equals to 2, we would get 2 clusters with 3 and 5 belonging to one cluster, and the 1, 4, and 2 being the second cluster. So taking a step back, in both combinatorial algorithms as well as hierarchical clustering algorithms, sort of the examples that I've been showing, it's been pretty clear how many clusters were really apparent or existing in the data. But oftentimes it's sort of a big challenge for investigators to determine how many clusters they really see in their data. So to illustrate this even further, here's a simple example again with observations in the two-dimensional Euclidean space where if we apply clustering to this, we might say that we see strong clusters, these sort of green triangle and these orange circles. Pretty believable. Hard to say that this isn't true. Now, say we observe data that looks like this. We can, again, apply clustering, and we would say, okay, now, again, we probably believe that these two clusters are separate and say that these maybe might be true subpopulation differences. But suppose we observe something like this. We can, again, apply clustering. We can get our orange circles and our green triangles, but now we're not so sure about how strong those cluster differences are. This comes down to sort of a fundamental question people run into with clustering is clustering algorithms will always give you a partition in your data, but it doesn't actually give you an implication about how strong that partition is. So the idea with significance of clustering is really taking this idea of strong clusters, maybe clusters, not sure, and quantifying it using this idea of statistical significance so that we can get some sort of quantified numeric value that can give us a sense of how much we really see clustering versus not sure. And in this paper, we talk about statistical significance for hierarchical clustering, but in general, this isn't the first time people have thought about this idea of significance and clustering. Some of the other methods that have been proposed include SIGCLUST, and PVCLUST, all methods we talk about in the paper. The context which we decided to develop this method was working closely with people in genomics. So I had an appointment jointly in the Cancer Center at the University of North Carolina, where I worked closely with people who were looking at sort of sequencing studies and gene expression studies in biological problems. And in these cases, typically the investigator observes maybe tens or hundreds of samples if they're lucky, but each one has maybe thousands to tens of thousands of covariates or measurements on them. So we fall into sort of this realm where we have this high-dimensional problem where we have very, very few samples, where statistical modeling can start to become fairly difficult. So what we were looking to do was to sort of develop a statistical significance procedure that could be applied in both a hierarchical setting as well as this high-dimension, low sample size setting as well. And while SIGCLUST previously had been developed for this high-dimension, low sample size setting, it wasn't able to handle hierarchical problems. Was very flexible, able to handle hierarchical clustering, but not able to handle these high-dimensional problems. And PVCLUST, we simply just didn't see the power that we were looking to find in the application. Now, this was work that I did a couple years ago, but sort of to drive home the point that this is still a very relevant problem. Earlier this week, I don't know why, but I received print copies of Nature Methods, and I was flipping through, and they have a monthly column called Points of Significance, where this month they were talking about clustering. And the subtitle for that article this month was Clustering Finds Patterns in Data, Whether They Are There or Not. So this is still a very relevant question in the biological sciences. Clustering is still a very real tool that people use, and it's still a very big challenge to identify whether these clusters are real or not. So to sort of describe the method that we developed, this significance for hierarchical clustering, or SHC as we called it for short, it's really, like I said, this approach to testing in hierarchical setting that also can handle these high-dimensional problems. And the procedure, I'll sort of describe it in two parts. First, sort of this procedure as a test at each one of these nodes or these joins in the hierarchical tree or dendrogram. And then pairing that with this idea of controlling family-wise error rate across this entire dendrogram. So to get to the first part, this is sort of a typo. I apologize, actually. We sort of focus on squared Euclidean distance and use Ward's linkage. Ward's linkage here I failed to define, but Ward's linkage is essentially this linkage function that measures the reduction in variance that is accounted for by splitting a single cluster into two clusters. Okay, now getting to the actual test that we use. So at each node along the dendrogram, we test a very simple hypothesis, whether the subtree at that node follows a single Gaussian distribution or if it doesn't follow a single Gaussian distribution. So here we make sort of this big assumption that clusters are well defined and approximated by single Gaussian or normal distributions, and essentially test whether a subtree is a single cluster or not. The idea being that if it's not, then it's likely to contain multiple clusters. And the way that we go about measuring this is using something we call the two-means cluster index, which is essentially the ratio of the sum of squares if we split these clusters into two groups versus the total variability in that data. So you can imagine if there are truly two clusters, this numerator, this within cluster sum of squares, is going to be incredibly small and tight. And if it's actually from a single cluster, that this numerator is actually going to be fairly large. There isn't going to be good separation accounted for by the two cluster labels. So the idea is we calculate the statistics for our raw data and the clusters that we identified, and we compare it against what we might observe under the null. So under the null that the data actually came from a single Gaussian. Are we seeing good separation, tighter clusters than we would if we actually had data from a null Gaussian? So walking through that procedure a little bit more, again, taking this simple example, this single node here, What we first do is we compute that cluster index from that raw data, 2 means cluster index, as we defined before. Alternatively, we also considered using what you can call the linkage value, that height of that split. And then we estimate the null Gaussian distribution to this. And once we've estimated a null Gaussian to these observations, we can simulate thousands of data sets and then cluster each using the same hierarchical clustering algorithms and again calculate the cluster index for these simulated data sets. Then, finally, we take those simulated data sets cluster indices and compare that against what we actually observed to obtain an empirical p-value. So in this case, what we see is that we have strong statistical evidence that there is indeed a split in this data set from the p-values observed here. So I mentioned earlier that one of the great advantages of the method as well as the SIGCLUST method that had been proposed previously is that it's able to handle these high dimension, low sample size problems. So one of the challenges in high dimension, low sample size settings is even this null data or null distribution estimation problem of a normal with mean mu and covariance matrix sigma can be incredibly hard to solve because we simply don't have the degrees of freedom to solve this problem. So one of the great realizations of the original SIGCLUST paper was that a lot of clustering algorithms are actually mean shift and rotation invariant. That is to say, we don't actually need to estimate the original null distribution, but actually some mean shift and rotation variation of this distribution. So you can think we can actually go about estimating this null distribution without estimating the mean, and we can also estimate this null distribution's rotation. So one rotation that you might consider is taking the rotation along the primary directions of an eigendecomposition of this covariance matrix. And simply, instead of estimating the full covariance matrix, simply estimate the eigenvalues of the covariance matrix. Now, this reduces the problem to simply estimating p parameters, which correspond to the diagonal of that eigendecomposition, or the eigenvalues of that covariance matrix, but that still can be a challenge if p is much larger than n. So another thing that we do is we assume that this set of eigenvalues follows a factor analysis model. That is to say that there's actually only a few true dimensions of true signal, whereas everything else is just background noise. So we can simply estimate the small amount of background noise as well as these few high true signal dimensions, and then we can reduce it to a much simpler problem. And there's been previous ways that have been described for estimating the small amount of background noise as well as this low rank diagonal true signal that have been presented in other papers, and so I'll sort of skip that for now and leave it for discussion if people have questions. So now that we've described the test that we've proposed, now the question is, how do we actually apply that test at each node to the entire dendrogram? So the way that we propose doing this is in a manner that will control the family-wise error rate. And we apply this sort of family-wise error rate correction that was originally proposed in Munchausen et al. 2008 in the context of significance testing when you have variables in a regression problem that are organized hierarchically. So again, with family-wise error rate control, what we want to do is we want to control the probability of at least one false discovery or false positive along our testing scheme. So the way that this procedure works is we want to control at a level alpha. What we do is we essentially reject at each node only if its parent node was rejected and if the p-value is less than alpha corrected by the proportion of the entire sample that is in that subtree. So just to illustrate, if we use a significance threshold of alpha, the first test is whether the p-value at that top node is greater than or less than alpha. And if we reject, the next set of tests that we perform is first between this pink and orange set of clusters on the right, we test if it's greater than or equal to alpha corrected by 2/3, which is the size of that subtree. And down in the bottom left, in the blue, we test against a threshold of 1/3. And so this procedure helps us correct for family-wise error rate by applying sort of essentially interpreted as sort of a Bonferroni type correction at each one of these tests. Okay, And finally, just to wrap things up, we also derived some theoretical and empirical results to support these methods. In the theoretical results, what we essentially wanted to do was characterize the behavior under both the null hypothesis and the alternative hypothesis. Essentially, in the null hypothesis, what we wanted to do was just to verify that our procedure is able to maintain level. That is to say that the p-values are true p-values when the null distribution or null assumption of a single Gaussian is indeed true. And it sort of follows very simply from the probability integral transform, simply because we apply this test that's based on calculating p-values from an empirical distribution of the statistic. And then on the alternative, what we wanted to do was show that the test is well powered to detect significant clusters when there really are clusters. And so how we do this is we first show that the clustering algorithm that we use, in this case Ward's linkage clustering, is consistent asymptotically, and then we also provide more conditions to show that our test indeed has p-value equal to 0 with probability tending towards 0 as n and p both tend towards infinity. And finally, I think the biggest amount of effort that we had to make was the simulation study. So going back and forth with the reviewers, we actually were able to improve our simulation studies substantially, and we considered a pretty large class of simulation settings. We chose simulation settings with number of clusters 1 through 8. We tried various different dimensions of the problem. We tried simulating data from different clusters, normal, slightly heavier-tailed, and much heavier-tailed distributions, as well as sort of changing the sizes of these clusters as well as the orientation and the separation of them. And what we did was we compared both our sort of SHC method using the 2 means cluster index and linkage index as a measure of strength of clustering against PV-clust as well as the previous proposed BOOTclust method. And so for each simulation, we replicated this 100 times and essentially looked at how well we were able to identify the true number of clusters and how long it would take the methods to complete. So in the null setting, this is just an illustrative example. In the table, what you'll see is a comparison of the SHC method against PV-clust and BOOTclust. And what we'd like to do, because this is a null setting, is verify that we don't get too many false positives. What we found was that PV-clust in low dimensions had some trouble, as well as BOOTclust in higher dimensions, but the SHC approach was able to maintain its level at all dimensions. And in terms of computational time, again, SHC seems to do much faster than both the PV-clust as well as the BOOTclust approach. And so the reason why we have these dashes for the BOOTclust approach in the high dimensional setting or 1,000-dimensional setting was simply BOOTclust would just not complete. We were unable to get it to give an answer for these higher dimensional problems. And similarly, when we applied this test to sort of null distribution or distributions that were generated from heavier-tailed samples, we observed generally similar trends. Now, in the alternative setting, we just looked at simulating from clusters of size 5, 6, 7, and 8 here. In the low dimensional setting of 10, we again calculated the number of times we were able to detect the true number of clusters. And what we see is that in the low dimensional setting, BOOTclust actually does as well as SHC, if not a little bit better, while PV-clust actually is unable to identify the true number of clusters. In computational time, SHC again does much better. And if we take this up to higher dimensions, again, while BOOTclust did well in lower dimensions, didn't show as much power and simply just could not be run in these higher dimensional settings. So finally, what we did was we applied this to a couple real data sets, namely these gene expression studies, simply because those were the applications that we were finding to be most relevant. And this was a collection of samples from the UNC microarray database. This was 337 breast cancer samples and 1,645 gene expression measurements. So what I'm showing here is a heat map where the rows are genes and the columns are samples. So red is high and blue is low expression here. And the original data set came with 5 intrinsic subtypes which had been previously determined, and we applied our SHC procedure to this data set. And what we were able to find was 3 significant clusters. Unfortunately, we weren't able to find all 5, And sort of if we look at this tree, what essentially happens is that because of the family-wise error rate correction, we simply aren't able to detect significant clustering and separation at the lower trees in this dendrogram. So I guess in this paper, what we've done is we've presented this SHC approach, which I think is great because it sort of provides this approach to assessing statistical significance in hierarchical clustering, which takes advantage of sort of the nested structure of this tree, as well as sort of these, it gives an interpretable, well-tuned, I suppose, output that makes it easier to understand sort of how the clustering is done. And I think it's a useful tool. Hopefully people will be able to use it. I've made it available as an R package, and hopefully I'm looking forward to hearing any sort of feedback on the approach and the implementation. Thank you.
Thank you very much, Patrick. That was a very clear, very easy to follow, very well described description of your paper and how you develop these statistical significance for hierarchical clustering. Thank you very much for that presentation. Right. So before we go to any questions from the people attending the Journal Club, we're just going to have a couple of slides where we're going to get a couple of thoughts on this from Jaakko Neuvelainen, who is just going to present a sort of discussant's view of presented. Jaakko, are you ready for that?
I'm ready. Thank you, Jim. First of all, thanks to Dr. Kimes for giving his talk to this Journal Club. I'm not personally a great expert in clustering problems, and therefore my discussion is more of a list of questions that arise while reading this paper and listening to your talk. In general, I think that this is a very clever idea to bring structure to a testing problem that seems very unstructured by definition. So clustering any data set without any assumptions it has little or no structure. And the way they do it is they use a hierarchical tree structure, and at each node of the tree they check whether the observations would arise from a single multivariate normal distribution. And I think this is clever. And the way I see it, you would end up with a dendrogram that is at each node. You would cut down the tree to the face where you reach the point when the clusters are no longer significant. So they no longer those nodes would deviate from a single multivariate normal. And by doing this procedure sequentially, the procedure holds its family-wise error rate, which is of course important. And in a way, you can think of the final tree as a fit with a finite mixture of Gaussians on the data. So you have at nodes you have distributions that fail to deviate from a single normal. So that's just a number of clusters times single multivariate normals, which is the finite mixture of them. But it arrives to the solution by the hierarchical procedure, and I think it's also relatively cheap to compute in this way. Now, having said all that, I personally work with register data, which has not that many variables, but a lot of individuals in the data. And my experience with hierarchical clustering with such data is that the speed of the algorithms is terrible. They are very slow. So when I think about adding testing via this procedure on top of that, my assumption is that the testing part itself is not that heavy computationally. It's the computation of the dissimilarity matrix and the clustering algorithm, but not the testing, because it's fairly simple to simulate from those normals once you have the covariance matrix right. This is one thing that came into my mind. Another thing which I may comment at this stage is that if you think about the final solution as a mixture of normal distributions, could you sort of build an overall metric to measure, like perhaps a likelihood type of metric, to measure how well your clustering has done? Because one thing with hierarchical clustering is that there are many algorithms available, and it's hard to know which one produces the right or the best result in any way. So
I see.
Perhaps this view could be used for such a purpose.
I think that's so there's a couple of things that I'd like to respond to. First regarding the speed of the testing procedure versus hierarchical clustering in general. I think, unfortunately, one limitation.
Hello. Has that microphone on? Please, could you make sure you turn your microphone to mute if you're not speaking?
Thank you, Jim. Sorry, getting back to the response. I think one limitation, unfortunately, of the method is actually it is limited by how slow hierarchical clustering can be when you have large samples. Here, sort of the p-value calculation relies on simulating data from the null distribution and then applying hierarchical clustering to those simulated data sets to obtain a sort of empirical distribution of the cluster index, the measure of the strength of clustering. And in that sense, it sort of requires applying hierarchical clustering to these sort of null data sets of similar size an incredibly large number of times. So I think, unfortunately, the limitation of hierarchical clustering for large data sets is an inherent limitation of this significant testing procedure as well. And I think another thing to mention actually is while in a lot of the simulations that I ran and we presented in the paper, the SHC approach does outperform other methods, but I think there definitely are settings where you have lower dimension but much larger sample size, where other methods like BOOTclust actually might be more appropriate. So SIGclust makes this assumption of a Gaussian or multivariate normal distribution defining clusters incredibly well, but this might not always be true. But it's a nice approximation to use, especially when you have very few samples in a high-dimensional space. But when you have a lot of samples in lower dimensional space, it might make more sense to use a more complex notion of clusters. And I think methods like BOOTclust allow for that sort of flexibility as well. So I think it's definitely not necessary to say that the method that we propose is the best in all cases, but I think there are definitely sort of considerations that should be or can be made to decide which tool or approach is best.
Okay, thank you very much for your response, Patrick. Jaakko, did you have anything more to say from your side?
Yes. How am I doing with time? I have plenty of comments, which I can skip perhaps some of them.
We'll give you a couple more minutes, maybe 3 or 4 minutes.
Okay, so maybe I'll go on the last points I had. So I've seen people to use clustering at very different applications in various ways. So one of the ways people seem to use it, hierarchical clustering in particular, is to use the somehow condense the information into explanatory variables and represent them as factors in your regression model, or vice versa, you cluster your outcome and then use those as outcomes in a regression model. This procedure.
আমেরিকা থেকে বলছে, নর্থ ক্যারোলাইনা, ভিডিও কনফারেন্স বায়োমেট্রিক থেকে।
Hello, could you introduce yourself with your name?
I think it might have been somebody who forgot to mute their mic, but yeah, I think that's a good point. I think one of the benefits of methods like clustering is it's good for doing sort of maybe lower rank approximations or reducing the dimensions of problems as well. And I think this definitely could be approached to help doing that, sort of using this idea of significance to determine which clusters might be appropriate for joining and observations to bring together. And I think, yeah, and definitely different applications beyond what I've presented as well.
Yeah, and one of the applications also would be, I think, I'm not sure what your view would be, but in sequence analysis where people use hierarchical clustering for grouping sequences, that's currently used, as far as I can see, only as a descriptive tool. Would this approach be appropriate for bringing more formality into sequence analysis? What would be your thought on that?
I think that's an interesting point. I think there's been a lot of discussion in statistical communities as well as communities that use statistical procedures about the importance or the irrelevance of p-values, and I think this sort of comes down to a much larger discussion about how we view p-values, their importance in really interpreting results of procedures. And I think here I only presented methods that sort of calculate p-values, or this idea of statistical significance to assess clustering, but there's definitely a large class of other methods as well which use sort of more heuristic type approaches for determining best number of clusters or optimal number of clusters, which I really haven't addressed. But I think a lot of those kinds of procedures as well, I think, have had a lot of success. So I think it ultimately comes down to what the practitioner is looking for as their final result. Are they trying to make a claim about how significant something is, or are they simply trying to find the best solution regardless of the significance of that best solution?
Okay, I think what I'll do is try and open up this discussion to the other members of the audience at the moment. I'm sitting here with some students, and they asked me, is this just about Gaussian distributions? And I think you've already answered partially that. Or what other distributions could the distance matrix cater for? And I've just seen a question on the board from Andreas Kraus, and I'd like him to ask that as well. And then perhaps if there's any other questions, you can ask them, and we'll get Patrick to come in at various points to respond to those. Andreas, did you have a question? Hello? Is it possible for Andreas to ask his question? Or shall I ask it as part of my role? If so. Andreas had a question here. How robust are the results against the parameters for hierarchical clustering, i.e. the distance metric and the linkage function, which I think is what you've already had some response to. Patrick?
Yeah, so I think that's a really good question. So a lot of the development that are presented in the paper and I guess in the presentation today is based on using Ward's linkage with squared Euclidean distance. So fundamentally, the method relies on this assumption that you have a mean shift and rotation invariant metric that you're using for your clustering, and that's sort of just a necessary assumption to make the parameter estimation more feasible in high dimension, low sample size settings. So there's a lot of different metrics that you could use and linkage functions that you could use, sort of the average linkage, max linkage, min linkage, I guess which people call complete or single linkage, which are also rotation and mean shift invariant. But there are definitely cases, I think I mentioned this also in the paper, like correlation-based distance, which is actually fairly popular, which doesn't actually sort of satisfy this rotation and mean shift invariance. So for those kinds of metrics, the method just can't be used as it's currently implemented. But definitely, I think there are some extensions that we could do to the method to make those sorts of classes of non-invariant metrics and linkage functions still work. But there definitely are other options as well. Sort of if you don't have high-dimensional data, you have a lot of samples, you can still use other methods like the boot-clip approach. And definitely, there's no harm to also trying the PV-clip approach as well.
International biometrics
Hello. Sorry, I'm not quite sure who's coming in on that with that comment. Thank you, Patrick, for your comments. Can members of the Journal Club, ask the questions directly? If so, please give your name beforehand and then ask your question.
Hello, I'm Prem Narayan from USA.
Thank you.
Firstly, I would like to compliment Patrick for. Hello.
Yes, carry on.
Hello.
First, I'd like to compliment Patrick for a very concise presentation of his paper. Secondly, I would like to raise a question regarding the breast cancer data, where the sample size of 337 were divided into 5 subsets based on the 1,645 gene expression data. I was wondering whether this was done before this clustering into 5 or it was done afterwards.
Very good question. Was it confirmatory or exploratory? Yes.
Yeah.
This is, I suppose, more of a confirmatory application. So these 5 molecular subtypes were originally described in a paper, I think that came out around 2010, possibly. So these are sort of 5 molecular subtypes that were well defined and well known, and we were sort of interested in seeing how well we could recapitulate and sort of significantly identify the different clusters, just solely based on gene expression.
Yeah. So if you had taken the whole total sample of 337, perhaps you would have got different dendrograms and different clusters, isn't it?
So here we do use all 337 samples.
I see. The other point is that your this example, very interesting example on gene expression data, had these dimensions of 1,645 gene expressions, you see. Whereas the simulations that you have done, they have all mostly, if I understand, 1,000 variants, you see.
Yes.
So probably there is probably a need to do simulations for a larger variable set, to fall in line with the gene expression situations where the p-value is going to be much larger. Here you have taken only about 1,500. So.
Okay, thank you. So let's get some questions from other people as well.
Okay. Thank you very much. Thank you.
No, thank you.
Nancy Geller, can you ask it, or do you want me to ask it? Do you have a question?
Me? Do you hear me?
Nancy, yes.
So my question is that the sample size within each cluster is actually random, and do you consider that at all? And does it matter?
Okay. Very good.
Good question. That's a good question. Here we actually don't consider the sample size in each cluster to be random in the sense of the clusters that are being tested. So when we test at an individual node and the subtree at that node, say, has 226 samples, we sort of take that 226 to be fixed. And we don't really sort of treat that as something that was randomly generated in a sense. An interesting question. I think that's a good question about whether it matters or not. I sort of thought about this a bit in that when we test at a subtree, we don't consider the fact that that subtree is part of a much larger data set that we've already split it off from, and that some of those observations might have come from a separate cluster that's been split off or might have been lost to another one. So I think that's a good point, and it might matter, but it hasn't actually been addressed in this. And I think that's sort of a limitation of the testing at each split rather than testing the entire tree, which I think is a distinction that I guess I should be making.
Okay. John Hind had a question about impact of background noise. John, do you want to ask it?
Yes, thanks, Jim. Can you hear me?
Yes.
Yes.
Because your testing procedure is basically using Gaussian distributions, I was wondering what happens when you have the situation of outliers or a very noisy, highly variable component over the other mixture components that you may have. What's the impact on your testing procedures then?
That's a good point. I think the background noise is actually a pretty important factor to account for. So there's been a couple different methods that I haven't really described here for estimating that background noise. And what we found was if we underestimate that background noise, what might happen is, or actually if we overestimate that background noise, we essentially aren't accounting for enough variability in the data, and sort of high levels of background noise can really throw the p-value calculation off in these high dimensional settings, because even if we're off slightly, if we're looking at thousands of dimensions, right, it sort of accumulates when we split something into two clusters, because clustering things into two things is essentially splitting it along the direction of highest variance. And if you have a lot of dimensions of even just a little bit of noise that can all work together to sort of stretch that single direction of most variability and really start causing things to be, misestimated in the calculation of that p-value. So it's really actually a fairly important part, and that we actually had to make some adjustments to how the background noise was being estimated, which we describe a little bit in the supplement.
Okay. Thank you very much, Patrick. And Philip Dixon has a question about silhouette-based methods. Philip?
Thank you. So, again, congratulations on a very concise and informative presentation. To follow up on your comment to Nancy's question, which is your testing procedure only considers the pair of clusters that are involved in any particular join, which to me seems to be a fundamental difference from silhouette-based methods, which evaluate within cluster dissimilarity to the nearest observation from any cluster. And I wondered if you'd considered or knew or had any insight into the relationship between your approach and not formal, very much more informal, silhouette-based method.
I think that's a good point. Thank you. I think fundamentally it is a very clear limitation of the method is it really doesn't evaluate the strength of clustering at the entire dendrogram level simultaneously. And I think methods like silhouette, the silhouette measure sort of do give a much more informed sense of how the entire tree splits into, say, more than two clusters. I think in terms of the relationship, I think it's hard to say. I'd say most things in clustering, I would say, are sort of complementary in a sense that because we're doing such exploratory work, it's always best to take different approaches. I think the one benefit possibly of taking a significant space approach is you sort of are able to account for the variability in the data a little bit better than sort of simple sort of metric-based approaches like Silhouette. I think, yeah, that's probably the most I can say off the top of my head.
Thank you.
Yep, thank you very much, Patrick. So time for one more question, if anyone has a question that they'd like to ask. Just to say that it seems to me that this is a very interesting, new approach to how to estimate the significance. But I mean, it's not going to be perfect for every situation. So time for one more question, if anyone wants to raise anything. Otherwise, I'll say thank you all for your comments, and I think that this was a very interesting and clear explanation, which I found very interesting. And so what I'd like to say now is this Journal Club will close at this point, and we'd like to invite you to the next one, which will be in August. I think, is it the 10th of August? I can't remember now the exact date. And I realize that some of you will be on your holidays, and hope you have a good holiday, but hopefully there'll be enough members to come for the next one, and we'll select a paper, and if you have any favorites that you think you would like to see presented on this Journal Club, please let me know. You can email me with my email address on the website. Thank you very much again for Patrick for his good, clear explanation. Thank you for Jaco for his discussant's role and to present a few questions. And thanks for the organisers in IBS headquarters for hosting all of this. Thank you all for attending, and I'll hope to see you in August.
Thank you.
Bye-bye.
Thank you.
Thank you, Patrick.
No problem.